two classes will deal with data compression, and in this lecture we'll be talking about basic concepts underlying data compression as well as Huffman coding. We've spoken about computational complexity in quite a lot of detail previously in this course, and we focused so far mostly on time complexity in terms of asymptotic complexity and big O notation. And what we're dealing with in that context is how quickly does an algorithm execute. Now, the second aspect of computational complexity, which we've mentioned here and there previously, but we haven't really focused on until now, is space complexity, which deals with how much memory does an algorithm require. Now, we can reduce time complexity through the design of better algorithms, as well as by taking existing algorithms and then optimizing their operation somehow. Space complexity in a similar fashion can be reduced by designing better data structures and also by means of using data compression techniques, which we'll be focusing on in this lecture and the next. The first thing we need to do is define what we mean by data compression. So let's do this by means of a simple analogy. Let's assume that we have a number of pillows and we need to ship those pillows somewhere, but we have to pay per box that we send. So obviously the fewer boxes that we send, the less money we have to pay. And what this indirectly means is that the more pillows we can fit into a single box, the better for us. So if we can squeeze then all of the air out of our pillows, then we can fit more pillows into a single box, meaning that overall we have to use fewer boxes, which means we have to pay less money. So once we then have our pillows arrive at our destination, we can then remove them from our box, fluff them up again, and then they will be in the same state that they were in before we sent them. So data compression then essentially is the process by means of which we can squeeze air out of our pillows. More formally defined, it involves getting rid of the irrelevant parts of data which can be restored fairly easily after we've transmitted our data to a particular destination. A concept that is very closely related to data compression is the notion of information. But what is information? Well, there are many different definitions for the term information. For example, if you were to ask an information scientist, they would give you a different definition to what we would typically use in computer science. But for our purposes, we can say that information is the meaning that is associated with data. Now, of course, there are many different kinds of data that we might want to represent, ranging from numerical data to textual data to more complex kinds of data like image and video data. One example, for instance, is a sequence of yes-no responses to a question. So we could then use textual representations by means of strings to represent the yes and no responses. Another representation that we can use is an encoding where we use 1 values to represent yes responses and 0 values to represent no responses. Now, in terms of these two sequences, we can see that while they use different representations, they in fact contain exactly the same amount of information because both of them have exactly the same meaning associated. So data compression then attempts to maximize the amount of information that we can represent per bit. Now, how many bits then do we need to store information? Well, we obviously want to use as few bits as we possibly can. So let's look at our previous example with our yes-no responses. And we can see then that we have a set of symbols that we want to represent where the symbols are either yes or no. So we can, of course, then use one single bit to represent these values, where this bit can take on a value of 1 or 0. And the encoding then that we use is that 1 represents a yes response and 0 represents a no response. Now, this is a fairly simple example, but we may have more symbols that we might want to represent. So, for example, if we're talking about the weather on a particular day, then we might have 4 symbols representing the values sunny, rainy, cloudy, and foggy. Now, we may use then a numeric representation to indicate these possible symbol values, where a 0 corresponds to a sunny value, 1 corresponds to a rainy value, 2 corresponds to cloudy, and 3 finally corresponds to foggy. So in this case, then, we can say that the number of symbols that we're representing is 4. So in other words, the value of n is 4. And we can then compute the number of bits that we require to represent these values by computing log base 2 of n, which is log base 2 of 4, which gives us then 2 bits. However, what if we want to go even further and represent more symbols? So let's say we want to represent all of the letters within the standard Roman alphabet, of which there are 26. Well, we can compute the number of bits that we would then require per character by using exactly the same kind of calculation. So here n is a value of 26, and we can then compute log base 2 of 26, giving us 4.7 bits required. But of course, we don't have the concept of fractional bits, so we need to round this value up to 5 bits. And we can immediately see then that there is a bit of redundancy involved here, because for 5 bits we can represent values up to 32, which is much more than 26. So we have a little bit of redundancy coded in here, which should immediately imply to us at this point that we can perform some kind of compression on this representation. So the question then is, can we do better than this 5-bit encoding for each character? The next concept we need to discuss is entropy. So entropy is a measure that we encounter in a lot of fields. For example, physics and chemistry talk a lot about entropy. But in essence, entropy is a measure of unpredictability, surprise, or chaos. So the higher a system's entropy is, the more unpredictability, the more surprise, or the more chaos that system has. And vice versa, the lower our entropy is, the more predictable, unsurprising, or non-chaotic the system is. So in our context, we can then consider entropy to actually be a measure of information. So let's look at this concept then in terms of a practical analogy. Let's suppose that we have a bag, and this bag contains red and blue marbles. So then we remove a random marble out of the bag, and the question then is, how unpredictable or surprising is the selection of the marble in terms of whether it is red or blue? So let's assume then that the bag holds an equal number of red and blue marbles. How surprised then would you be by the color of the marble that you randomly pull out of the bag? Put another way, can we predict what the color will be? Well, basically, if we know that the number of red and blue marbles is equal within the bag, then essentially we have an equal probability of selecting a blue marble or a red marble. So what this means then is there is no way that we can predict up front whether the marble that we pull out is going to be red or blue. So in other words, there's a fairly high level of unpredictability, which means that the system, in terms of the bag that contains the marbles, has a very high level of entropy. Considering another example, let's assume that we know that the bag only contains blue marbles. How much unpredictability is there in this case? Well, we know that there's a 100% chance that any marble that we pull out of the bag will be blue. So in other words, we can predict then with 100% certainty that the marble will be blue in color. So in other words, in this case, the bag has a very low entropy, because there's a very high level of predictability within the system. Entropy then also exists on a continuum. So if we assume that we have a bag that holds mostly red marbles, but there are 1 or 2 blue marbles mixed in within that bag, then we can say with a relatively high level of certainty that the marble that we will pull out will be red, but there is a chance that the marble might be blue. So in this case, we then have a system that has a relatively high level of entropy. It doesn't have as high a level of entropy as the bag that contains an equal number of red and blue marbles, but it also then does not have an entropy that is as low as the bag that only contains blue marbles. Now, if we assume that we will be using sequences of bits to represent codes for symbols, as we did on the previous slide, it is also natural for us to assume that we could use different lengths of bit codes for different symbols within the same encoding scheme. So, for example, one symbol might be represented by a single bit code, whereas another symbol might be represented by a 4-bit code. Now, in this context, we are interested then in computing the minimal average length of these various bit codes that we would be using within our encoding scheme. Now, we can compute this value using Shannon's entropy, and over here we have the formula for computing Shannon's entropy. So in this formula, S then is a set of n independent events, and in our context we consider events to be symbols that we need to encode. So in other words, there are n different symbols that we need to then be encoding by means of bit sequences. We also have the set P, and P then contains all of the probabilities of these n events. So we have a probability for each of the events, meaning that P contains the same number of values as the set S. Pi then in this context represents the probability of event I. So we can see that the entropy then is computed by means of a series summation, and we perform the summation over all of these Pi values, meaning the probabilities for each of the n independent symbols that we will be encoding. So then the value h of s is the entropy that we compute for the set S of symbols that we are working with. So in this formula then, negative log base 2 pi is then the minimum number of bits needed to represent symbol I, which occurs with the probability of p subscript I. So in this formula over here then, we have negative log base 2 p1, and that is then the minimum number of bits needed to represent symbol 1 with probability p1. Alright, so let's look at this computation then in terms of our first simple example. For this example, we have our set S, which contains the two symbols that we need to encode, yes and no. And we will then assume that yes and no have an equal probability of occurring. Now, over the set P, we then represent our probabilities as fractions, and these must all add up then to 1. So in this particular case then, we have the set containing the values 0.5 and 0.5, and what this means then is that the symbol yes has a 50% chance of occurring, whereas the symbol no also has then a 50% chance of occurring. So if we then plug these probability values into our entropy formula, then we get the following computation that we need to perform. And we can then use a neat trick to compute log base 2 of 0.5. So log base 2 of 0.5 is equivalent to log of a half, which we can rewrite as log base 2 of 2 to the power of -1. And then using the basic rule for computing the log of power, we then get a result of -1. So if we then plug this value into our formula, we get then the following computation, which then boils down to 0.5 plus 0.5. And these 0.5 values then are equivalent to the minimum number of bits needed to represent each of these two symbols, one for yes and one for no. So we see then that the value that we've computed is 1, which means that the entropy then of our encoding scheme is 1. And to interpret this value, we would then say that the amount of information within our encoding scheme is 1 bit, or in other words, we can use 1 bit value to encode all of the symbols that occur in our set S. Over here then we have a table that summarizes these values. So we have then our two data values, yes and no. Each of those have a probability of 0.5, and then we can use an encoding of a single bit for each of these values, where we can assign a value of 1 to yes and a value of 0 to no, or potentially vice versa. Let's now compute the minimal code length in terms of entropy for our second example. So here we have our set S, which contains the symbols that we need to encode, namely sunny, cloudy, rainy, and foggy. And then we also need our set P, which contains the probabilities for our various symbol values occurring. So again, we have fractional values stored within this set, which we interpret as percentages. And we can see if we add all of these fractional values together, we get a total of 1. So the way we would interpret these values is that the value sunny has a 50% chance of occurring, cloudy has a 25% chance of occurring, and rainy and foggy both have a 12.5% chance of occurring. Here we have our formula for computing the entropy, just for reference purposes. This is the same formula we used on the previous slide. And if we then plug our probability values into this formula, this is what we get. And again, we can then use the same trick to calculate the values for the logs in this formula. So as we saw in the previous slide, log base 2 of 0.5 is equivalent to log base 2 of a half, which has a value of -1. And in a similar fashion, log base 2 of 0.25 is equivalent to log base 2 of a quarter, which we can rewrite as log base 2 of 2 to the power of -2. And based on the standard rule for logs of powers, we get a result of -2. Then finally, log base 2 of 0.125 is equivalent to log base 2 of 1/8, which we can rewrite as log base 2 of 2 to the power of -3, which has a value of -3. So we can then plug these log values into our formula, which we've done over there, and the final result is 1.75. So what this means then is that the information content for our encoding scheme is 1.75 bits per symbol on average over the encodings for all of the symbols within the set S. However, bits, as we've mentioned before, are indivisible. So in other words, we can't use 1.75 bits for each of the encodings for the symbols in the set S. So we can obviously then just round this value up to 2 bits, meaning that we use 2 bits to represent each symbol in S, and we then get the following table. So over here we have then our various symbol values, sunny, cloudy, rainy, and foggy, along with their probabilities. And if we then use 2 bits for each of the codes, we could then use a code of 00 for sunny, 01 for cloudy, 10 for rainy, and 11 for foggy. Obviously, we could use these codes interchangeably for any one of the particular symbol values. So for example, we could have used the code 00 for cloudy, as long as all of these encodings are distinct. However, this obviously isn't optimal because what we are doing now is we are using 2 bits for each of the codes rather than the optimal 1.75 bits per each of the codes for each of the symbols in our set S. So the question then is, can we get closer to this optimal value of 1.75 bits per symbol using some other kind of encoding? So if we want to come up with an encoding that compresses our entropy, then we first of all need to calculate the minimum average bit code length, just as we did on the previous slide in terms of entropy. Then what we need is an encoding that gets us as close as possible to this minimum that we've computed. Now, not every encoding is a good encoding. Not all encodings are equally good, and there are some encodings that won't even work. So we need to define some properties for an optimal encoding that actually works and gets us close to this minimum that we are aiming for. And there are 4 such properties, so we'll look at these one by one. The first property is a relatively trivial one. Each code in our encoding scheme must represent exactly 1 symbol. So over here we have an encoding for 2 symbols, yes and no, and we can see that we have a code of 0 for each of those. Now, this obviously doesn't work because we now have an ambiguous coding scheme. In other words, if we see a 0 value in our encoding, then we don't know whether this bit value indicates a yes or a no value. So this is an inappropriate encoding in terms of our first property. An encoding that would work would be as follows. So here we have again our 2 symbol values, yes and no, and now we've given a code of 0 to yes and a code of 1 to no. What this then means is we have a unique code for each of our symbols, so a 0 can only represent yes and a 1 can only represent no. We could have obviously used the opposite encoding with a 1 representing a yes and a 0 representing a no. So this encoding scheme then is appropriate in terms of the first property for an optimal encoding. Moving on to the second property for an optimal encoding, we have what's referred to as the prefix property. And this states that no code should be a prefix of another code. Now, to see why this is important, let's look at an example. Over here we have a bit-based encoding for the symbols sunny, cloudy, rainy, and foggy. Now, what's important to notice here is that this encoding violates the prefix property. And this is because we can see that the code for sunny, which is 0, is the prefix, the beginning of the code for rainy. In a similar fashion, the code for cloudy, which is 1, is also the prefix of the code for foggy. So if we look at this encoding then, and we interpret this bit sequence over here, 0, 1, 1, 0, 0, 1, 0, we could then interpret it as 0, which is the code for sunny, then 1, which is the code for cloudy, followed by 1, which is again the code for cloudy, and then 0, which is the code for sunny. But we can also then interpret this bit sequence as 0, 1, which is the code for rainy, followed by 1, 0, which is the code for foggy, followed by 0, 1, which is the code for rainy, and so on. So what we see then is that we have an ambiguity. We have 2 potentially valid ways of interpreting the same bit sequence. And in fact, there are other ways that we could also interpret the same bit sequence given this encoding scheme. Now let's consider the following coding scheme over here. So again, we have the same symbols, sunny, cloudy, rainy, and foggy. And we can see very importantly in this encoding scheme that none of the codes are prefixes of any other code within this encoding scheme. So what this means then is if we consider exactly the same bit sequence as we did for the previous encoding, we can then only interpret it as 0, which is the code for sunny, followed by 110, which is the code for rainy, followed by the code 0 for sunny, and then 10 for cloudy. So this means then that our second encoding scheme satisfies the prefix property, and what this essentially then means is that it ensures an unambiguous decoding of any particular bit sequence. We can now move on to the third property for an optimal encoding, which states that for any two codes A and B, the length of code A may only be less than or equal to the length of code B if the probability of code A is greater than or equal to the probability of code B. What this means in simpler terms is that codes that occur more often should be shorter codes in terms of the number of bits that they consist of. So let's look at this example encoding over here. Once again, we have an encoding for 4 symbols: sunny, cloudy, rainy, and foggy. And what we see then is that this encoding violates our third property, because the longest two codes, the codes for sunny and cloudy, which are each 3 bits long, will be used a cumulative total of 75% of the time, whereas the shorter codes will be used only 25% of the time, which wastes a lot of space that is available to us. This means that this encoding scheme then is not optimal, and in other words, we should then not use this encoding scheme. Now, if we look at this alternative encoding scheme over here, we see that the third property is maintained. So, for example, we can see that sunny has a code length of 1, which is shorter than the code lengths for all of the other symbols within our system, and that is because the probability of sunny is higher than the probabilities for all of the other symbols occurring. So what this means then is that the longest codes are used the least, whereas the shortest codes are used most often within any particular encoding. This then means that this encoding scheme does satisfy our third property, and therefore it represents an optimal encoding. We're now ready to consider the fourth and last property of an optimal encoding. And this property is a little bit more complex than the previous 3 properties. So the fourth property states that every short code must be used either as a standalone code or as a prefix for a longer code. So let's look at what this means in terms of this example encoding, again for the symbols sunny, cloudy, rainy, and foggy. Now, the short codes that we need to consider are codes that have a shorter length than the longest codes that exist within this encoding. So we can see that the 2 longest codes each consist of 4 bits, which means that we need to consider short codes that consist either of 1 bit, 2 bits, or 3 bits. Now, it's also important to note that the short codes that we consider are all subject to property 2, which is the prefix property. So the short codes for this example that we need to consider are 0, 1, 10, 11, 110, and 111. Now you'll notice that none of the short codes that we consider start with 0 except for the short code 0. And the reason for this is that the prefix property means that we can have no codes within this encoding that start with the code 0 that are longer than a single bit. However, we can consider the short code 1. We can also consider the short code 10, but again, no other codes are allowed that start with the code 10. So we exclude then any 3-bit codes that start with 10. We can also consider 11, and then 110 and 111. And that then includes all of the short codes that we potentially might consider. Now, what we notice here is that the majority of these codes are included as standalone codes or as prefixes. So, for example, the short code 0 exists as a standalone code. The short code 1 exists as a prefix for these 3 codes. The code 10 also exists as a standalone code. 11 exists as a prefix for these 2 longer codes over here. and then 111 exists as a prefix for this last code over here. However, what we see is that the code 110 is not used as a standalone code, and it also does not appear as the prefix of a longer code. So what this then implies is that this encoding scheme has codes that are longer than they need to be in order to encode the symbols with the given probabilities. And we therefore are wasting space and using more bits than we require for our encoding, which means that it's not optimal. Now, if we look at this encoding over here, the short codes that we need to consider, again subject to property 2, are 0, 1, 10, and 11. And what we see then is that all of these codes are used either as standalone codes or as prefixes. So again, the code 0 is used as a standalone code over there. The code 1 is used as a prefix for these 3 codes over here. 10 is used as a standalone code, and 11 is used as the prefix of the 2 longest codes. What this then means is that this encoding satisfies the 4th property, which means then as long as it satisfies the previous 3 properties, it is then considered an optimal encoding. So those are the 4 properties that must be satisfied for us to have an optimal encoding. And now the question arises, how are we then going to construct such an optimal encoding? So what we'll be using in this lecture is what's referred to as the Huffman encoding algorithm to generate a bit-based encoding of a set of symbols with associated probabilities. So the algorithm's operation is relatively simple. For each symbol that we need to encode, we create a tree that consists only of a single root node where that root node is the symbol. We then repeatedly execute a while loop, and we keep doing this while more than one tree exists in our set of trees. And for each iteration, we take 2 trees, T1 and T2, which have the lowest probabilities, Pt1 and Pt2 being the probabilities of those 2 trees. We then make trees T1 and T2 the left and right children of a new tree that we construct, which we will refer to as T, and then we set the probability of this new tree to the sum of the probabilities for the trees T1 and T2 that we've set as the children for the new tree T. So once we've then generated a single tree through the merging of all of these subtrees eventually, we then associate 0 values with all of the left branches in this tree and 1 values with all of the right branches in the tree. Then for each symbol S within the tree that we need to encode, we traverse from the root of the tree to the leaf node of that particular symbol, and we concatenate all of the 0 and 1 values along the traversal path from the root to the symbol that we're trying to encode. Let's now apply the Huffman coding algorithm to our previous example. So in this table, you can see the 4 symbols that we need to encode, as well as their associated probabilities. The first step is that for each of these symbols, we need to create a tree with a single root node, which we've done over here. Each of these nodes contains the probability for the symbol associated with that node. Next, we need to repeatedly merge trees until we end up with one single final tree. At each of the merging steps, we take the trees with the 2 lowest probabilities, and those become leaf nodes for a new parent node, which then contains the cumulative probability of the 2 children. So the first 2 trees that we need to select are the trees for rainy and foggy, because they have the lowest probability values of 0.125 associated with each of them. We merge those together into a new parent node which contains the cumulative probability, in other words, the sum of 0.125 and 0.125, which is 0.25. We then select the next two lowest probability values, which are 0.25 and 0.25, and merge those together to create a parent node containing the cumulative probability of 0.5. Finally, we merge the last two remaining trees, which each have a probability of 0.5 associated with them, creating a root node with a cumulative probability of 1. Now we need to associate a 0 value with each of the left branches within the tree and a 1 value with each of the right branches in the tree. Now we're ready to generate a code for each of the symbols by tracing a path from the root to the leaf node associated with that symbol. So for Sunny, we trace the path from the root node down to the leaf node for Sunny, and we see that the only binary value that we traverse is the value 0, meaning that that is the code for Sunny. Next, we move on to Cloudy. So we start again at the root node. We traverse to the node containing the probability 0.5, and then down to the leaf node for Cloudy. And we see that we have traversed the binary values 1 and 0, meaning that we concatenate those values into the code for Cloudy. Then we move back again to the root node, and now for Rainy, we traverse from the root to 0.5, then 0.25, and finally to the leaf node associated with Rainy. We see that the values that we've traversed over are 1, 1, and 0, which we concatenate to create the code for Rainy. And then we repeat the process for Foggy, starting again at the root, moving down to 0.5, then 0.25, and finally the leaf node for Foggy. We see that the binary values that we've traversed over are 1, 1, and 1 again, so we concatenate those to form the code for Foggy. So now we have an encoding for each one of our 4 symbols. The next question that we want to answer is, how well does this encoding perform? So in order to answer this question, we first of all need to consider the minimal average bit code length that we calculated previously. So we saw on a previous slide that the value that we computed there was 1.75, meaning that in the optimal case, we should use an average of 1.75 bits to encode each of the symbols. Now notice that each symbol has a multiplication associated with it. And in each of these multiplications, the left factor then is the probability associated with that symbol, whereas the right factor is then the number of bits hypothetically that in an optimal situation would be associated with that particular symbol. So we can use then that same principle to calculate what the actual average bit code length is for the encoding that we've generated, which we do over here. So we multiply then for Sunny, its probability of 0.5, with the number of bits for Sunny's code. In other words, there's 1 bit used in that code, so we have 0.5 multiplied by 1. For Cloudy, we multiply its probability, 0.25, with the number of bits for its code, which is 2, so we have 0.25 multiplied by 2, and we do the same for Rainy and Foggy, which you can see in these 2 multiplications over here. So if we then compute the result of this encoding, we see that we achieve then a value of 1.75, which is the actual average bit code length for the encoding that we've generated. And what we notice is that this value is the same as the minimal average bit code length that we computed for the optimal case. So what this then implies is that according to entropy, we've in fact achieved an optimal encoding, and we actually can't do better than the encoding that we've generated here. So now as a question for yourself, consider this Huffman coding algorithm, which is iterative in nature because it uses a while loop, and try to determine whether you can re-implement this algorithm, but instead use a recursive implementation. So a recursive implementation is provided in the course textbook, but don't look at that implementation. Try to work it out for yourself and then compare the implementation in the textbook to your implementation. Let's consider another example of the application of the Huffman coding algorithm. So here the table summarizes the symbols that we want to encode. We've got 5 symbols, A, B, C, D, and E. And over here you can see the probabilities associated with these 5 symbols. So first of all, we need to generate a tree for each of the symbols. And then we need to perform repeated mergings until we end up with a single tree. So we select then the 2 lowest probabilities for symbols D and E, being 0.16 and 0.15, and we merge those together into the parent node containing the cumulative probability of 0.31. Next, we merge the trees for symbols B and C, which have the lowest remaining probability values of 0.17 for each of those, into one parent node with a cumulative probability of 0.34. Next, we merge 0.34 and 0.31 to create a parent node containing the cumulative probability of 0.65, and then the final 2 nodes that we merge create a parent node with a cumulative probability of 1. Next, we associate zeros with all of the left branches within the tree and ones with all of the right branches. Then we need to determine the encoding for each of the symbols, tracing from the root. So we trace from the root down to the leaf for symbol A, which gives us an encoding of 0 for A. Then for symbol B, we trace from the root again, getting an encoding of 1, 0, and 0. And then for C, starting again at the root, we get an encoding of 1, 0, and 1. And for D, again starting at the root, 1, 1, 0. And finally, for symbol E, again starting at the root, we get an encoding of 1, 1, and 1. Alright, so now we've generated our encoding, and now once again we want to determine how effective and optimal this encoding is. So again, we need to then compute the minimal average bit code length in terms of the entropy. So I won't run through the entire calculation, but if we plug in the correct probability values, then we get a value of 2.2328. So what this means then is, in the optimal situation, we should be using an average of 2.2328 bits for each of the codes that we use for the 5 different symbols. So next we need to calculate what the actual average bit code length is. And we do this exactly the same way that we did in the previous example. So if we then perform this calculation, we see that the final value that we end up with is 2.3, meaning that our encoding that we've generated here uses an average of 2.3 bits per symbol encoding. So what we see here now is that we have not managed to achieve the minimal average bit code length. We have an actual average bit code length that is slightly higher than the minimum value that we've computed. So what this means then is, according to entropy, this Huffman coding falls a little short of the optimal compression performance. This is not due to a mistake during our encoding. It is just, in certain situations, impossible for us to generate an encoding, at least using a code for each individual symbol that manages to achieve the hypothetical perfect performance. Now that we've considered the operation of the Huffman coding algorithm, let's look at how we would actually implement the algorithm. Now, there are obviously a wide variety of different ways that one could approach this implementation. However, a fairly commonly used approach is to use a doubly linked list, where each linked list node contains a tree, and we sort this linked list according to probabilities. So over here we have our doubly linked list in its initial form. We can see that we have a list node for each of the symbols, and each list node contains a tree, where each tree is, of course, a single root node, and we have then the list nodes ordered according to probabilities, with the lowest probability values on the left and the highest values to the right. All right, so then we need to perform a series of merges. So at each iteration, we will then take the first two nodes within the linked list, which of course must be the nodes with the lowest probabilities. And we retrieve then the trees from those two nodes, and we merge them, creating a merged tree, which we then store in the second node. We then move the second node to the correct location within the linked list based on its merged probability, and we delete the first node. Now, we could obviously have done this the opposite way around. In other words, we could have placed the merged tree into the first node and then delete the second node, but deleting the first node is a simpler operation than deleting a subsequent node, so usually this is the way that we would approach it. So here we have then the first merge that has been performed. We have now merged the trees for symbol E and symbol D together into a single tree, and we have placed it into the correct location within our doubly linked list. This is then the second merge that we perform, the third merge, and finally we end up with a single node in our linked list that contains the complete tree. Next, we then need to determine the encoding for each of the symbols, which we do as we saw on the previous slide, and that then gives us our full encoding for each of the symbols. Now, of course, the linked list needs to be ordered somehow, and there are once again a variety of different ways that we could approach this ordering. But a fairly natural way of achieving this is by means of a priority queue, where the queue's priority is based on the probability values that we have computed. We could also use a min heap, and as we've seen, a min heap stores the lowest value, in other words, in our particular implementation, the lowest probability, as the first element within the heap array. What this means, however, is that we need to restore the heap property twice. Firstly, we need to restore the heap property after removing the first node, and then we once again need to restore the heap property after updating the second node's probability. You can refer to the textbook for more details on what an actual implementation of a heap-based method would look like. Now, any compression algorithm implies the existence of a sender and a receiver. The sender is responsible for taking data in its original form and performing an encoding operation which produces a compressed version of that data. The receiver is responsible for performing a decoding operation which should produce the data in the original form that the sender started with. Now, in the case of Huffman coding, the sender then is responsible for generating the Huffman coding tree, as well as the codes associated with each of the symbols that could appear in the data that needs to be compressed. So in this case, we will assume that the sender is trying to generate encodings for the same set of symbols as we discussed in the previous example. So over here then we have our Huffman coding tree, as well as the codes associated with each of the symbols. Now the sender needs data that has to be compressed, so we will assume for this example that the sender wants to compress the word bead. Notice that the word bead consists only of letters that appear as symbols within our encoding scheme. So now to perform the encoding, we follow a fairly simple set of steps. We just run through each of the symbols within the data that we want to compress, and we perform a lookup in the table that we've generated, and then retrieve the code associated with that symbol. We then concatenate that code into the compressed version of the data that we are generating. So in this example, we start off then with the symbol B. We look up the code 100 that is associated with the symbol B, and we add that to our encoded data. Next we move on to E, so we retrieve then the code 111, which we add to our compressed data. Then we move on to A, so we retrieve the code 0 and add that to our compressed data. And finally, we move on to D, where we retrieve the code 110 and add that to our compressed data. So now we have a compressed version of our original data. Notice that if you look at the number of symbols that are used, it looks as though the bit sequence is longer than the word that we are trying to encode. However, we have to remember that on a typical system, letters are encoded and typically at least 8 bits are used per letter. So this means that our encoded bit sequence is much shorter than the number of bits that would be used to represent the individual characters directly. Right, so now we need to send this compressed version of the data to the receiver. However, it turns out that unfortunately Huffman trees are not necessarily unique. And this is because different trees are built whenever there are several valid merge options that could be used at any particular point during the construction of the Huffman coding tree. So what this implies is that we must also send the Huffman code tree to the receiver. Now notice that this tree does not need to include the probability values because the receiver is not interested in those probabilities. However, the structure of the tree needs to be transmitted as well as the 0 and 1 values associated with each of the branches. Now we need to perform a decoding operation. So this decoding operation works by running through each of the bits in the encoded version of our original data from left to right. And we begin then at the root of the tree and we perform a traversal down the appropriate branch for the bit value that we've retrieved from our encoded data. We then continue this traversal until we eventually reach a leaf node, and then the symbol associated with that leaf node is added to our decoded data. We then move back to the root node of the tree again, and we continue performing this process until eventually we've exhausted all of the bits in our encoded data. So we start off then at the root, which we've highlighted in red over there, and then we begin with the leftmost bit, which is 1. So the 1 indicates that we need to traverse to the right of the root node, which we've done over there. Then we discard that bit and move on to the next bit, which is 0. This indicates we need to traverse to the left, so we move then down another level, discard the 0 bit, and we move on to the next 0 bit, which means that we need to traverse to the left of that node. So now we've reached a leaf node, and we see that that leaf node is associated with the symbol B, which we add to our decoded data. So now we discard the 0 bit and we move back to the root of the tree again. Now we continue processing bits one by one, so we now have a 1 bit, meaning we traverse to the right of the root node. We discard that 1 bit. We move on to the next bit, which is a 1, so we traverse to the right and discard that 1 bit. And then finally we have another 1 bit, meaning we traverse once again to the right. We've now reached a leaf node, which is the leaf node for the symbol E, which we then add to our decoded data. And we move back again to the root of our tree. So now we move on to the next bit, which is a 0 that indicates we have to traverse to the left of the root node. And we now immediately reach a leaf node which is associated with the symbol A, so we add A to our decoded data. We then discard the 0 bit and once again move back to the root of our tree. And now we move on to the next bit, which is a 1, meaning we traverse to the right. Discard the 1 bit, move on to the next bit, which is a 1, so we traverse once again to the right. Discard that bit, and the final bit is 0, meaning we traverse to the left. We've now once again reached a leaf node, and that leaf node is associated with the symbol D, which we then add to our decoded data. So now we see that we have decoded the compressed version of the data that has been produced by the sender, and this decompressed data, the decoded data, is exactly the same as the original data that was sent by the sender. We'll close this discussion by considering one way that we could improve the efficiency of a slightly underperforming Huffman encoding scheme. So we're going to look at this example over here where we are working with three symbols, A, B, and C, and these are the probabilities associated with the three symbols. So we'll generate our Huffman coding tree in exactly the same way as we did before, by merging pairs of nodes and then associating 0 and 1 values with the branches of this tree, and finally then extracting encodings for each of the three symbols. So now we're interested in determining how well this encoding scheme actually performs. So we do this in exactly the same way as we did in the previous example. We calculate the minimal average bit code length, which we compute as 1.1568, which means then in a hypothetical optimal encoding scheme, we would use an average of 1.1568 bits per symbol. We then move ahead and compute the actual average bit code length based on the actual encoding that we've generated, and we see that we get a value of 1.3, meaning with this actual encoding that we've generated, we require an average of 1.3 bits per symbol for our encoding. So we can then compute the efficiency of this encoding scheme by taking our minimal average bit code length, which is 1.1568, and dividing that by the actual average bit code length of 1.3, and that gives us a percentage of 88.98%. What this means is that our encoding scheme then manages to achieve 88.98% of the efficiency of the hypothetical optimal encoding scheme. This is not too bad, but let's see if we can improve this efficiency. So what we will do is, instead of generating an encoding for individual symbols as we've just done, we will now generate an encoding for pairs of symbols. So in other words, we need to consider every possible pair of our symbols that we might need to encode. So every possible pair then includes the pairs AA, AB, AC, BA, BB, BC, CA, CB, and finally CC. So we will generate then an encoding for each one of those pairs, where we treat each pair as a separate symbol. Now we need to compute then probabilities for these pairs, and we do that by means of computing the product of the probabilities of both of the symbols that are used in the pair. So for example, for the pair BC, we would compute then the combined probability as 0.2 multiplied by 0.7, and that gives us a result of 0.14, which is the combined probability. This kind of multiplication is based on standard probability theory. So what I've done here as well then, just to make the tree a little bit neater and easier to follow, is I've ordered these pairs according to probabilities, with the smallest probabilities on the left and the highest probabilities on the right. So now we just proceed as normal and build our Huffman coding tree. So first of all, we merge the pairs AA and AB. Notice that AA has a probability of 0.01 and AB has a probability of 0.02, which produces a cumulative probability of 0.03. However, we could just as easily have merged AA with BA and produced the same cumulative probability. So this is an example of a point where we have two mergers that are equivalent to one another, and these would result then in different Huffman coding trees. Right, so we continue then with our mergers as follows. And again, here we can see that we've merged the probability 0.09 and 0.14 to produce a cumulative probability of 0.23, but we could also just as easily have merged with the leaf node for the symbol BC, or for the symbol CB, because both of those also have probabilities of 0.14. So we continue then with our mergings, and eventually we've generated a full tree. We associate zeros and ones with the branches of this tree, and then we generate encodings for each of the symbols, where each symbol is a pair of the original symbol set that we considered to begin with. Right, so again, we're interested then in the efficiency of this tree. So we can again then compute the minimal average bit code length, which we compute as 2.3136. What this means then is that to encode a pair of symbols, we would then need to use an average of 2.3136 bits. Now notice that this value, 2.3136, is different to the value that we computed originally, which was 1.1568. And the reason that this value is larger is that we are encoding two symbols at a time as a single unit, whereas in the first case we were encoding only a single symbol at a time. So now we compute the actual average bit code length, which arrives at a value of 2.33, and we can already see that the value of 2.33 is much closer to the hypothetical optimal performing encoding that we've computed. So we can once again then compute the efficiency of this second approach by taking the minimal average bit code length of 2.3136 and dividing that by the actual average bit code length of 2.33, which gives us a value of 99.30%. What this means is that by combining our symbols into pairs, which we've created separate encodings for, we've managed now to achieve 99.3% of the optimal performance. This is, of course, a lot better. So we have managed to create then a much more efficient encoding scheme. However, what's important to understand here is that we've improved the efficiency of our compression. However, this is at the expense of a larger tree. So what I'd like you to consider at this point is, why would a larger tree present a potential problem in a practical setting? Think of this in the context of a sender and a receiver, as we discussed previously in this lecture. All right, so that concludes then our discussion on the basics of data compression as well as Huffman coding. In the next lecture, we'll move on to adaptive Huffman coding and then finally run length encoding.